some discrete probability distributions. Before we have seen what a random variable is, we have seen what is the expected value. We have seen so far what is a discrete random variable, and we will understand that better, the difference between discrete and what we are going to define as continuous later when we see later continuous distributions or continuous random variables. By now, let's focus on discrete distributions. The random variables on the distributions can be determined by its probability distribution, or in the case of the discrete case, their probability mass function. I mean, they can be classified by their formulas, by its formula. So here we are going to see some of them. First, we start with the binomial distribution. We say that x is a random variable with a binomial distribution if its probability mass function or PMF is given by this formula. We say that a random variable has a binomial distribution if its PMF, probability mass function, or probability distribution is given by this formula, this one here. But of course, from the mathematical point of view, we can classify very well what is a binomial distribution. If we know that the probability for any value of x, by the way, here x goes from 0 up to n, we can classify that as binomial if we know that for each value of x, the probability is computed by using this, right? I mean, you substitute here x and compute all of this, and you will have a probability. We know that that random variable we have or has a binomial distribution, but of course, what is the meaning for this? I will try to explain how to interpret when you have to apply or you can model a given situation by using a binomial distribution, and the other distributions we will see. Here, essentially, you can use a binomial distribution when you have an experiment that only results in two outcomes. success or failure. The experiment is repeated. N times. The trials are independent. And the probability of success in only one trial is given by P. B, X, and P will return the probability of occurrence of X successes. So the binomial distribution essentially is you have one experiment that has only two outcomes, success or failure. You repeat the experiment a finite amount of times, n times, and we are assuming that from one trial to one time to another one, there is independence. What is the meaning for that? Remember that essentially, intuitively, independence means that what happens in one trial doesn't affect what could happen in the other one. So essentially that. The experiment is repeated n times. We know the probability of success in only one trial is P. Then if you have that, the binomial distribution will give you the probability of that you observe in those n trials, the probability you observe X successes. Oh, by the way, the expected value for X for a binomial distribution is MP, and the variance is MP times 1 minus P. So, example. One typical example, tossing a coin. But here we're going to toss a coin 3 times. And let X be the number of heads. So, can we model the distribution for this random variable X, number of heads when we toss a coin? Oh, I have to say this. Fair coin. Toss a fair coin. Toss a fair coin 3 times. Let x be the number of heads. Can we say that in this case we have a binomial distribution? I mean, the distribution for x is going to be binomial. Well, let's see if the requirements are met. First, we need to identify one experiment that has only two outcomes. That experiment could be only tossing the coin. When we toss a coin, we have only two outcomes, head or tail. So yes, we have only one. On the only experiment repeated only once, it has two outcomes, head or tail. But here the experiment is being repeated, in this case 3 times. And do we know the probability of success in only one trial? Yes, the probability is, if the coin is fair, the probability is 1/2 or 50% or 0.50. So yes, we can model this with a binomial distribution. But when you are going to do that, and for the upcoming distribution we will see here, usually you will have to identify the parameters. What do I mean? What do I mean by that? Anything that is not the x, like in this case n and p, you need to know that. I mean, those are going to be fixed values for this specific problem. What is going to be variable is going to be the x. So here we need to identify n and p. In this case, n is equal to 3 times, and p, the probability of success in only one trial. I mean, when you make only one toss, since we have a fair coin, the probability is 0.50. So we already have the parameters n and p. Now we can use the binomial distribution. For example, at x equal to 0, what is that? Substitute into this formula. So we will have b 0, 3, comma 0.5. And this is going to be 3, 0 times 1 minus 0.5 raised to the n, that is 3, minus x, that is 0. And if you compute, oh, by the way, remember, if you forgot what this is combinations. Combinations, 3 choose 0. So this is equal to, if you can use your calculator to compute that, this is going to be 1 times 1 minus 0.5 raised to the 3, or what is the same, 0.5 raised to the 3, and this is only 0.125. Or what are the same in fractions, 1 over 8. So how can we interpret this? The probability that we observe 0 heads when tossing a coin 3 times, a fair coin 3 times, is what? 1 over 8. Probability of observing 0 heads when tossing a coin 3 times is 1 over 8. What about, for example, at x equal to 1? 1 head, again, is going to be, use the formula. Replace the x by 1, but the values for n and p are going to be the same. 3 and 0.5. And the formula becomes 3 combination choose 1 times 1 minus 0.5 raised to the 3 minus 1. 3 combination choose 1. This is going to be 3 times 0.5 raised to the square. And this is going to be only 3 times 3 3/4. No, wait a second. Oh, I'm sorry. Yeah. I'm sorry. I forgot something in the formula. In the formula for the binomial distribution, yeah, I forgot something. You have to put also p raised to the x. So n minus x, p raised to the x. So here would have to be p raised to the x. The result for the first case, for the first, when x equals to 0, is not going to change because this is going to be p, that is 0.5 raised to 0. And that is, but that is only one. So the answer is correct, this one, even with this. Yeah, I'm sorry. Again, I forgot to put this, right? The right formula is all of this. With this. So here I have to put p raised to the x. So this becomes 1 minus 0.5 raised to the 3 minus 1 times p, that is 0.5 raised to the 1. So this becomes 0.5 raised to the 1. So this becomes 3 times 0.5 raised to the 3. Or what is the same? 3 over 8. You see? And so on. We can also verify that for x equal to 2, we will have the value that we know, 3 over 8, and for x equal to 3, we will have the value 3 over 8. By the way, of course, you can use this, you can verify this by hand if you use the formulas I'm giving to you here. The first formula we're seeing here, this one. Of course, if you substitute the values here and you get the and you do the computations, you are going to have, and you do it well, you do it correctly, then of course you can get all the answers we're going to be seeing here, like this one and this one, unlike the ones that I did here. But of course, we can take advantage of technology and to simplify simplify the computations. I will recommend in this case for this section, for this particular video, I'm going to recommend the application, this one. Look at the top, probability distributions. This application might be very useful for this video and the next one, or when you want to compute the probabilities and instead of using the formula, you want to use, you can use this, right? Let's verify our answers. Look, here we have several distributions. The one we're seeing right now is the one that is binomial. So click there, binomial. By the way, this application is for free, right? Again, its name is probability distributions, like the title in the top, binomial. And then you will have to specify the parameters. Sometimes the symbol for the parameters used here in the application might be different with the one that we have in the book or in the notes, but no problem. Just be sure that you identify which is which. So in this case, notice how we have the same symbols, n and p. So in my case, n is equal to 3, p is equal to 0.5. And let's verify, for example, the case x equal to 0. So you type x equal to 0 and choose here in the fourth box, be sure that you have probability of x equal to x, because we have other cases, probability of x less or equal and probability of x greater or equal. Maybe we can use that later, but by now, only here we have probability of x equal to x. Look at the value in the box. Look at the value in the box in red or pink is 0.125. That is the same value I obtained here, 1 over a, 1.25. You can verify this for x equal to 1 as well. Only replace the x by 1. And then done. 0.375. 0.375 is this, 3 over 8. Yeah? So if you want to use this application, I recommend to do it. Just be sure that for examples, the example we're going to be seeing here, you identify the parameters. In this case, they were 3 and 0.5. All right, let's see one example from the book, from Weckberg. I will explain what this is a binomial. I will identify the parameters, and then I will use the application. Okay. It says, in the game of roulette, the steel ball is rolled onto a wheel that contains 18 red, 18 black, and 2 green slots. If the ball is rolled 21 times, find the probability of the following events. Part A. Probability the ball falls into the green slots 5 or more times. So for the part A, notice here, we can think of this as a binomial distribution because the probability that the ball falls into the green is going to be 2 slots out of 18 plus 18 plus 2, 38, 2 over 38, and the experiment is repeated 21 times. So P is equal to this, and N is equal to 21 times. Why this is a binomial? The experiment is being repeated, right? The experiment is, the success here is going to be whether we observe a green slot, and we are repeating this 21 times. The probability for success is 2 over 38 in only one trial. And this has been repeated, and N is equal to 21. But the question here is probability of green slots 5 or more times. So essentially here, we look for probability that x is greater or equal than 5. How can we compute this if we're using the formula? Well, if you want to use the formula, you will have to substitute x equal to 5, 6, 7, 8, 9, 10, 11, 12, and so on up to 21. You will have to substitute all of these values into this formula, into this one, yeah, and then add all the probabilities. But we don't have to do that here, right? Because we can take advantage of the application. This is probability of x equal to 5, plus probability of x equal to 6, and so on, after the probability of x equal to 21. So we have to compute all of those probabilities and add them. But again, here we can take advantage of the application. So go to the application. Here N is going to be 21. P, I think this application doesn't accept fractions. If you want to put 2 over 38, I mean this here, I think it's not possible. 2 over 38. No, you see, not accepted. So how to avoid that? Well, we have to turn this into a fraction first, into decimals first. So 2 over 38 with decimals is 0.052631558. And then for x, choose the value of 5. X equal to 5. Here, be careful. In the fourth box, don't choose probability of x equal to x. Choose probability of x less or equal, no, greater or equal. The probability is 0.004040. .004040. Well, actually, this one you can see here, right? So it is right. For the part B, the ball doesn't fall into any green slot. So again, here we have probability of success. We're talking about green. Probability of success in only one trial, in only one roll, is 2 over 38. And n is the same, n equal to 21. But here x is no green slot. That means x equal to 0, right? So we want probability of x equal to 0. And this is what? Go again to the application. Change the x by 0. But change the fourth box by equal. The probability is 0.32129. It's the same here, right? Part C, the ball falls into black slots 12 or more times. Part C, in this case, we're talking about black slots. How many black do we have? We have 18 red and 18 black. So here the probability of success in only one trial is going to be 18 over 38. And n is the same, equal to 21. And here x is going to be 12. And we look for probability of x greater or equal than 12. So this is going to be n equal to 21. Change the probability. In this case, it's going to be 0.47368421. And x equal to 12. And we need greater or equal. Put 0.248. This, you see? 0.2485. And then what about the part D? The ball falls into red slots 10 or fewer. So in this case, please verify that by yourself. I will let you know that here P is the same. The probability of red is 18 out of 38. N equal to 21. X equal to 10. But we're looking for the probability of X less or equal than 10. So substitute that into the application, and you're supposed to have this value. B, C, and D. All right. All right. The other distribution. Negative binomial. We say that x has a negative binomial distribution if its probability distribution or probability mass function is given by x r comma p and is equal to x plus r minus 1 combination 0 minus 1 r minus 1 p raised to the r to the r times 1 minus p raised to the x for x equal to 0, 1, 2, and so on. And what is this for? Is noted the name, negative binomial, and before we saw binomial. So is this related to the binomial distribution? Yes, it is. So the negative binomial distribution returns the probability of observing x failures before r successes. So here, oh, I'm sorry, here x goes from r plus 1 and so on. Well, this distribution gives you the probability of observing x failures before r successes when you are performing an experiment that is a binomial distribution. An experiment that is modeled by a binomial distribution. So I wanted to see the difference because both they have the name binomial. In the binomial case, X is the number of successes. In the negative binomial case, X is number of failures before R successes are observed. So for one is the number of successes and the other one focus on the number of failures, or more, we can say that the binomial focuses on the number of successes and the negative binomial focuses on trials. Yeah. How many times do we need before we can see the second? Well, for example, when we toss a coin 5 times, how many trials do we need to observe, or at what trial are we going to observe the second head? Yeah, if for us success is head. The expected value of this is R times 1 minus P divided by P, and the variance is R times 1 minus P divided by P squared. So let's see one example of negative binomial from web work. It says a telephone saleswoman arranges a sequence of interviews of potential customers in order to sell them an insurance policy. She believes that her success rate in completing a sale in an interview is 11%. Provide answers to the following to 3 decimal places. Part A. What is the probability that she fails to make a sale on the first interview? All right, probability of making a sale is 0.11. Then probability of not making a sale is the complement for this, 1 minus 0.11. That is 0.89. Here in this part, we will need this. But now, notice this can be thought as a binomial first, because probability of not making a sale, this in this case, yeah, I know it sounds weird, but this not making the sale for the part 8 is like our success. The probability is 0.89. Probability E is 0.89. But here we have to identify the number of successes we want. What is the probability that she fails to make a sale on the first no, I'm sorry. No, I'm sorry. It's not asking for that, but well, P is equal to 0.89. Yeah, that is true. Yeah, so far so good. 0.89, the probability is 0.89. What is the probability that she fails to make a sale on the first 5 interviews? I think it says all of them. In all of them. So if we have independent events, if we have independent trials, the probability we look for is fail in the first interview, 0.99 times 0.89 times 0.89 times 0.89 times 0.89. Or what is the same? 0.89 raised to the 5. And if you do it, you will see that the answer is 0.558. This one here. Yeah, in this case, so far, we don't need any negative binomial. But for the part B, the question is, what is the probability that she makes her first sale on the 4th interview? Notice, first sale on the 4th interview. What do we have to do here? We need to identify the parameters. First sale, probability of sale is 0.11. Yeah, it's given by this. For what is the number of success? It says first sale. R is representing the successes. And X the failures. So we want the first success. So R equal to 1. Because we want the first success. We want the first success to occur on the 4th interview. So if the first success is going to occur on the 4th interview, then for the first interview, the second interview, and the 3rd interview, we won't have any success. So how many we will have failures, right? We will have 3 failures. So here X, we have to specify the X is the number of failures. In this case, it's going to be 4 minus 1 equal to 3. So these are the parameters. Why 3 again? Because we want the first sale on the 4th interview. How many failures do we need before that happens? 4 minus 1, 3. 3 failures. And X is supposed to be the number of failures before our successes. How many successes? The first one here. So the parameters are 0.11, 3, and 1. And of course, you can take advantage of the application. Of course, if you want to substitute into this formula, you will have the answer. But again, I'm going to be using here the application. Go to the application. Look for negative binomial. We have 2 versions for the negative binomial. I think you need to verify that it's the one that matches with our formula. I mean, both are equivalent. I think this is the one, right? The first one. Yeah. Notice how it matches with our formula. So yeah, we have to use this one. So specify success, R is equal to 1, P is equal to 0.11, and X is equal to 3. And then probability X equal to X, and the answer is 0.077. 0.078, you see, round it up. Equal to 0.078. For the part C, it says what is the probability that the second sale is made on the 8th interview. So again here, we're talking about the sale. The probability is 0.11. What is the number of success that we want? In this case, the number of success is the second sale. So R is going to be equal to 2. And we want this to happen in which trial? We want this to happen in the 8th interview. So how many trials before the 8th interview is 8 minus 1 equal to 7. Those are the parameters. So P equal to 0.11, R2, and X equal to 7. So R equal to 2, P equal to 0.11, and X equal to 7. And the answer is 0.0428. And I know that Weber said that the answer is 0. I think I have verified this answer. Yeah, and I can say that it's very likely, in my opinion, the answer from Weber is wrong. Yeah, well, usually happens. But this is supposed to be the right answer. So for this case, do not trust in the answer from Weber. If some of you are having problems for your version of this problem, let me know and I will give you the credit, okay? But try to follow the steps that I'm giving to you. All right. Other distribution. Hypergeometric. If X is the number of successes in a random sample of size n drawn from a population with a total of n, and there are m successes, then the probability of X successes is given by this formula. The expected value for this hypergeometric is n times m divided by capital N, and the variance is given by n minus n divided by n minus 1 times n times n times 1 minus m divided by n. All right. But well, what is this for? Hypergeometric distribution, it works when we have a total population of n items, yeah, capital N items. We take a sample of size lowercase n, but we know that among those capital N items, M of them, capital M of them, they have certain characteristic of our interests. I mean, that I call here success, yeah, in quotation marks. And you want to know, when you take the sample of size lowercase n, you want to know the probability that you have X successes, so X elements with that characteristic. The probability is this, yeah? Let's see one example. A biotechnology company produced 180 doses of somatropin. I'm sorry if I cannot pronounce this well. 188 doses of somatropin, including 11 which were defective. Notice, here we are given the information of the total 188 doses. This is the sample, the population. And we know that among them, 11 are defective. So here the characteristic or the success in quotation marks is defective. The feature of our interest, the characteristic of our interest is defective. So quality control tests 13 samples at random and rejects the batch if any of the random samples are found defective. What is the probability that the batch gets rejected? So in this case, again, we have to identify the parameters. Here, capital N, the total number of elements in the population is 188 doses. What is the size of our sample? That is lowercase n, is 13. And M, again, is the number of elements in the total population with the characteristic or feature that we want. In this case, we want to focus on defective doses. You see? Defective. So how many defective do we have? 11. So put 11. And what is probably that batch gets rejected? In this case, how do we know? Notice it said that if it is rejected, if we observe only one defective in our sample of 13. So in this case, X is going to be several values, either 1, 2, 3, and so on up to 13. But in this, so we will have to substitute into this formula. With these parameters, we have to substitute into this formula. Yeah? X equal to 1, 2, 3, and so on up to 13. But fortunately, we can take advantage of what? We can take advantage of, oh, by the way, this goes from X equal to 0, 1, 2, and in the worst case, up to M or up to N. So 1, 2, 3, and so on up to 13. Well, actually, the most we can have defective is 11, right? So it has to be up to M. All right, but if we want to do it by using this formula, we would have to substitute X equal to 1, 2, 3, and so on up to 11 in this case. Yeah, in this case because M is less than 13, so that's why we put M. So, but we don't have to do that. We can take advantage of properties of probabilities. We look for the probability that X is greater or equal than 1. but this is the same as 1 minus the probability that x is equal to 0. I mean, if we compute the probability of no defective and subtract this from 1, we will have what we're looking for, right? So use the application with these parameters, n, lowercase n, and m. Hypergeometric. Hypergeometric is this one. You see it? Almost in the bottom. Hypergeometric. Lowercase n is what? Is 13. Capital N is 188. M is 13. No, 11. 11 are defective. Yeah, 11. And we want 0. And the answer is 0.444491. So the answer is going to be 1 minus 0.444491. You see? I know the answer here is given because they are using the formula here. They don't have this. If you compute this, 1 minus 0.444491, the answer is 0.555509. But notice, I know that Weber had this. Where is this coming from? I mean, it's the same. The answer should be the same. They're computing here 1 minus the probability of zero defective, but by using this formula. So notice, if I substitute in this formula, we have 1 minus combination sum, that is 11, choose 0, because we want, because here x equals 0, right? 0 times n minus m. This is 188 minus 11. And at the bottom, n minus x, that is 13 minus 11, divided by the total, 188, choose 13. Combination, choose 13. Yeah, and follow with this formula. And this is the same they have, because they have 1 minus combinations 11, choose 0 is 1. So what is left only is 188 minus 11 oh, I'm sorry, this should be n minus x, so it should be 0. Yeah, I'm sorry. So 0 here, x, yeah, I'm sorry, n minus x. So 188 minus 11, 13 minus 0, 13, divided by combinations, 188, 13. You see? This is the same answer they have. But if remember, this symbol means combinations. That's why they have C. Combinations. But if you do it, you can do it directly in the application, and you will have this 1 minus this and this. One more, Poisson distribution. X has a Poisson distribution if its PMF is given by probability of x equal to x is equal to e exponential from the exponential function e times lambda, this symbol is called lambda, divided by x factorial for x equal to 0, 1, 2, 3, and so on. The expected value of x is lambda, and the variance of x is lambda 2. What is this for? This probability distribution returns the probability of observing a given event occurring x times. If you know the average for expected value of times the event occurs over a given period or interval. So, use the Poisson distribution if you know that something over a given interval or period, you know the average or expected value of occurrence for a given event, and you want to know the probability that event occurs a certain number of times. This distribution depends only on one parameter, only on this symbol is the Greek letter lowercase lambda, lambda. Lambda. It's a Greek letter. So let's see one example. Notice the number of accidents that occurred at a BC intersection is Poisson distributed. So it said that directly Poisson distributed with a mean of 4.9 per week. So Poisson, you're given the mean automatically. Lambda is equal to 4.9, and this is the parameter we need. 4.9 per week. Find the probability of the following events. Part A, no accidents occurred. So here, x equal to 0, no accidents. So what is that? So use the application, or you can use directly this formula if you want. This is the number e, or the exponential function raised to the evaluated at negative lambda. Lambda raised to the x, and this is x factorial. But we can use the application. So Poisson is the last one, you see? And it needs only one parameter, it's 4.9. And here x equal to 0, x equal to x, 0.007447. probability of x equal to 0 is 0.007447. And you can see the answer we have here, right? Well, this is with more decimals here. Part A, part B. In this case, 5 or more. So this is x equal to 5 or 6 or 7 and so on. Now maybe you wonder, when should we stop if we want to do this? Well, actually up to infinity, right? This is a mathematical model, and the assumption is that we should evaluate 5, 6, 7, 8, 9, 10, 11, 12, and so on up to infinity, right? How can we do that? Well, we don't need to do that. We can, if you want to use this formula here, you will have to evaluate this at 0, 1, 2, 3, 4, and subtract from 1, so you can have the complement that is 5, 6, 7, the probability for 5, 6, 7, and so on up to infinity. But well, in this case, of course, we can take advantage of technology. So probability of x greater or equal than 5, go use the same parameter lambda. So it's going to be 4.9, here 5, and choose greater or equal 0.541788. And you can realize the same as this, right? And the part C is a little bit tricky. The part C, one accident occurs today. So average accident, notice the average accident we are given is per week. So we need to compute, for this part, we need to compute this per day. So if we have one accident per 4.9 accidents per week, per day, divide this by 7. And it's going to be 0.7. You see? 0.7. So in this case, we have to use lambda for the part C, use lambda equal to 0.7, and we look for the probability that one accident, so x equal to 1 exactly. See, because it says one accident. So use these parameters, 0.7, 1, and equal 0.347610. 0.347610. This is the answer, and you can observe this is the same as here. All right, yeah, I understand that maybe this might be not very simple, so if you have questions, let me know. I will try to respond them during the weekend. If you don't have questions, I mean, of course, you don't have questions, right? See you in the next video.